Welcome to the Fundamentals of Hydraulics and Troubleshooting. This training program is the first in a series of lessons on hydraulics to provide you with the fundamentals of hydraulic systems. This program will cover the components that make up hydraulic systems and the common problems associated with their failures. Hydraulics provide man the ability to control enormous energy at his fingertips. Hydraulics is an integral part of most machinery. The same principles of design, operation, and troubleshooting apply both to large and small machines. Likewise, the design of just one hydraulic circuit in a large machine may be identical to the entire hydraulic system of a small machine. All hydraulic systems, whether simple or complex, contain the same basic components, namely a reservoir, a pump, control valves, lines, fluid, and an actuator, the device that performs the work. In addition to these basic components that are common to all hydraulic systems, some hydraulic systems utilize additional components for specialized tasks. From construction equipment, farm machinery, landscape equipment, hydraulic orchard pruners, to man lifts, manufacturing, warehousing, mining and refuse. Hydraulics are hard at work. Some hydraulic systems control only one or two functions and are relatively easy to understand. Examples of some common systems include horticultural pruning equipment, gang lifts on turf mowers, ditching machines, forklifts, and many other agricultural and industrial applications. The common components that make up a hydraulic system can look very different in size and shape from system to system. Because it is sometimes difficult to determine what function a component performs, it is helpful to have a diagram of the hydraulic system you are servicing. Just as electrical components are represented by symbols and circuit schematics, hydraulic circuits are also illustrated with symbols and schematic diagrams. Technical manuals expect the technician working on hydraulic systems to be able to read and understand hydraulic symbols and schematics. Before continuing, two important principles must be fully understood. First, hydraulic pumps cause oil to flow. Second, pressure results when a restriction in the system reduces that flow. Thus, pressure is caused only by a resistance to oil flow. As this circuit illustrates, the hydraulic pump is creating a continuous flow of oil. By closing the valve to restrict oil flow, pressure increases. Opening the valve reduces the restriction, thus reducing the pressure. If the pump flow is totally restricted, either the pump must stop rotating or the pump breaks, and all hydraulic functions stop. Keep this principle in mind at all times when analyzing hydraulic systems. Let's look at a complete hydraulic system and how its individual components work together. Throughout the remainder of this video, note the schematic symbol for each hydraulic component as it is shown. Hydraulic oil is stored in the reservoir and is moved through the system by the hydraulic pump and then returned back to the reservoir. There are two types of hydraulic systems, open-centered and closed-centered. The top circuit is called an open-centered system. It allows oil to be freely pumped back to the reservoir under very low pressure when the valves and cylinders are not being used and the spool is in the neutral or centered position. The bottom circuit is called a closed-centered system. Oil flow is stopped at the spool and pressure remains high at no flow. In this video, we will limit our discussion to open-centered systems. In an open-centered system, when the spool in the directional control valve is stroked, meaning pushed or pulled, hydraulic oil is directed to the piston in the cylinder. When the hydraulic force under the piston becomes greater than the piston load, the piston will move up until the spool is returned to the centered position or the piston in the cylinder reaches the end of its stroke. If the spool is not returned to the centered position, excessive heat will develop when high oil pressure is relieved through the system relief valve. Relief valves are installed in hydraulic systems to protect the system components from damage caused by excessive pressure. Relief valves limit system pressure by directing pump flow back to the reservoir. To reverse the cylinder direction of travel, the valve spool is moved to the opposite end of its stroke. The piston will stop when the spool is returned to the center position because the cylinder ports are blocked, hydraulically locking the piston. Before studying each of the components that make up a hydraulic system, let's review the precautions and dangers inherent in troubleshooting hydraulic systems. First, there are some things that should always be avoided. Never use your hands to find leaks. Use a paper towel instead. Oil injected under the skin could cause serious infection. Never disconnect implements in the raised position. They can come crashing down. Never weld on or near fittings or tubing. They will be weakened and become dangerous. To avoid injury, always follow these rules. Always read the service procedures before servicing or repairing a system. Always safely prop up any mechanism that must be serviced in the raised position before starting work. Always turn off the engine before disassembling any hydraulics. Always neutralize the hydraulic pressure in all lines and components before disassembly. Always remove the key and place a warning tag on the steering wheel so no one will start up the machine while it's being worked on. Always clean up spills immediately. Always properly dispose of used oil. Always wear protective clothing. Whenever appropriate, always wear a bump hat, gloves, safety glasses, goggles, or a face shield that meets ANSI standards. Stop the video here. Review the basic principles of hydraulic safety. Then continue with the major components that make up hydraulic systems. Hydraulic oil is highly refined to meet various applications. One machine may have a system with no special requirements for the hydraulic oil, while in another machine, the hydraulic oil must also serve as a lubricant for gears and bearings in the transmission or gearbox. These hydraulic oils might appear to be alike, but they are refined to different specifications. Some hydraulic oils may need to meet high temperature or transmission gear lubrication specifications, while others must be compatible with certain seal materials. Some oils are mineral-based, while others are synthetic or vegetable-based. Guessing about oils will usually bring on problems. Not following the manufacturer's hydraulic oil requirements and maintenance schedules is a major cause of machinery downtime that leads to loss of income and creates unnecessary expenses. The first component we will look at is the reservoir. Reservoirs come in many shapes and sizes. Well-designed reservoirs may have several features that aid in their performance, but might not be obvious at first glance. Some reservoirs have a sight glass on the side, so the operator can check the oil level. On others, a plug may need to be removed. Hydraulic reservoirs are designed to be filled 1/2 to 2/3 of their volume with hydraulic oil. 1/3 to 1/2 their volume is an airspace that allows for oil expansion due to heat and differences in oil volume when the piston and rod in the hydraulic cylinder are extended and retracted. The reservoir design shown here can be found on some applications, but will not provide the best service over a long period of time. Let's look at how a properly designed reservoir can improve the operation of a hydraulic system. Hydraulic oil returning to the reservoir should never be allowed to plunge into the reservoir, but should be returned beneath the surface of the oil to prevent air foaming. Foamy reservoirs caused by plunging hydraulic oil develop air cushions in the hydraulic cylinders, which make them bounce and give poor operator control. Air can also enter the system from low reservoir oil levels, and during hillside operations when the oil flows away from the reservoir outlet. To help prevent this, baffles are installed to reduce sloshing and stop air from entering the reservoir outlet. Reservoirs should have a breather cap, capable of keeping out dust, foreign objects, and water. In some cases, the breather cap doubles as a filler cap or as a pressure cap. To prevent contaminants from entering the hydraulic pump and the entire system, some manufacturers place a filter or screen at the reservoir outlet or in line with the pump. This is referred to as a suction strainer or suction filter. These filter screens are usually made of brass, plastic, or stainless steel. Having the reservoir outlet above the bottom of the tank will also help prevent contaminants from entering the system. Water from condensation, internally generated sediment from dirt and rust particles, and contaminants from the wearing of metal parts can mix with the oil in the reservoir. To help remove contaminants, some reservoirs have a low point drain that allows the operator to drain out any moisture, dirt, or rust. The diameter of the suction hose connecting the reservoir to the hydraulic pump should be much larger than the diameter of the pressure hose leaving the pump. A larger suction hose develops less restriction to oil flow than a small hose. Before we go on to discuss pumps, let's look at some common problems that can occur between the reservoir and the hydraulic pump. A major problem can occur when the suction filter in the reservoir becomes plugged. Excess vacuum is created in the suction hose. This causes a defective suction hose to collapse and cut off the flow of oil into the pump. A slow cylinder response and loud pinging or cavitation noise then occurs. Cavitation is the high-speed compression or implosion of negative pressure vapor bubbles as these bubbles go from the vacuum or inlet side of the pump to the pressure side of the pump. If these bubbles collapse near a metal surface, they will chip away particles of metal. Cavitation eventually leads to pump and system failure. As the chip particles pass through the system, they damage all the other components in the system. As a pump fails, the oil filter starts plugging with metal particles. Partially plugged suction filters decrease the flow of oil into the pump, further increasing cavitation destruction. Another problem occurs when air enters the hydraulic system on the suction side of the pump through leaky fittings or pump seals. The vacuum created from a hydraulic pump is so strong it is capable of pulling in air through gaskets and seals that do not appear to be leaking on the outside. Aeration resulting from incoming air can be just as destructive as the cavitation from the vacuum vapor bubbles. Additionally, air in the system slows down a machine's cycle time. If there is an air leak on the suction side of the pump, the oil in the reservoir will appear foamy. Additionally, if the oil appears milky, there's water in it, which will rust steel parts and cause them to fail. Some manufacturers install filters on the return line to the reservoir or on the pressure side of the pump. Always check the hydraulic schematic for the number of filters and their locations. To indicate when filter elements should be changed, some manufacturers provide differential pressure indicators or a warning light. These indicators are the best way to know when a filter needs to be changed. Regardless of where the filters are located, they must be changed on schedule or sooner in hot, dusty conditions. Stop the video here. Review the principles of hydraulic oils and reservoirs, then continue on with hydraulic pumps. Let's turn our attention now to hydraulic pumps and see how they operate. Gear pumps trap oil between the gear teeth and pump body and squeeze the oil out as the teeth come together. External gear pumps trap oil between the gear teeth and the pump body as the teeth rotate outwardly away from the pump inlet. As the trapped oil approaches the outlet, the gears mesh, forcing the oil out the pressure port. Remember, if the pump flow is restricted, the pressure within the system can jump from a few hundred to several thousand pounds per square inch. There are two types of internal gear pumps. One type uses a crescent-shaped separator that traps the oil between the gear teeth. A second type of internal gear pump is the rotary version or gerotor pump. Another type of pump, the vane pump, uses small vanes instead of gear teeth to trap the oil. Because the vanes are either spring-loaded or free-floating, they self-compensate for wear. There are two piston pump designs: axial piston pumps and radial piston pumps. The axial piston pump has cylinders that are lined parallel to the pump's driven shaft. Most piston pump circuits use a charge pump to pressurize the oil and force it into the piston pump. The pressurized oil then flows through a one-way check valve or charge port to fill the cylinders. As the pump rotates and the pistons reach the bottom of their strokes, the inlet check valve or inlet port closes. As the pistons rise, they push the oil out the outlet check valve or outlet port. The cycle is repeated as the piston cylinders again fill with oil. The axial piston pump varies its volume by adjusting the length of its stroke. This is done by reducing the angle of the swash plate the pistons slide on. As the angle decreases, the volume of oil pumped decreases. And as the angle of the swash plate increases, the volume pumped increases. There are several variations of the radial piston pump, but we will illustrate only one pump design. The radial piston pump has cylinders that point away from the center like a starburst. Some radial piston pumps vary their pumping volume through a differential pressure mechanism. When there is hydraulic pressure in the piston pump crankcase, the crankcase pressure pushes the pistons up in their cylinders to balance the charge pump priming pressure. Therefore, when crankcase pressure is reduced, the charge pump is able to push the piston downward in proportion to the reduced pressure. The lower the crankcase pressure, the longer the effective piston stroke and the greater the volume pumped. Variable displacement piston pumps are adaptable to many applications and are commonly used when the volume of oil pumped needs to be varied without changing the speed of either the pump or the engine. For example, in hydrostatic transmission systems, the engine and variable displacement piston pump run at a constant RPM. Ground speed is controlled by varying the oil output from the piston pump to the piston motor. Here are some important additional points about pumps. Pump shafts and pump bodies could break when relief valve pressure settings are increased above manufacturer specifications. Pump seals harden from excessively hot hydraulic oil. Pumps wear out from abrasives in the oil, such as rust particles, metal chips, and dirt. Pumps cavitate when the oil is too cold and viscous, or when the pump suction strainer becomes too restricted. Additionally, oil thickened by cold temperature may not easily pass through a partially plugged filter, and could cause the filter bypass valve on some equipment to open and release dirt and wear metal particles into the mainstream. It has been found from years of experience that many of the hydraulic pumps that are replaced during service are not at fault. Something else in the system is making the pump look defective. A restricted suction filter is a good example. Remember, if the pump can't get oil, it can't pump oil. Pumps can be accurately tested with a flow and pressure analyzer like this one. This type of testing is necessary for high-performance machinery. Look up the system's operating pressure and the pump's flow in gallons per minute. After the engine is warmed up, shut it down. Pumps must always be totally isolated from the rest of the system before they are tested. Anything downstream of the pump could cause it to look faulty. Isolating the pump is done by removing the pump outlet hose or tubing from the system and coupling a pressure gauge, flow meter, and control valve to the pump outlet hose. Next, a hose is connected from the control valve to the reservoir fill hole. Remember to always open the control valve before the engine is started, because there is no relief valve in the pump circuit during the direct pump test, and the pump drive shaft or housing could break from excess pressure if the control valve is restricted. If you encounter a broken shaft or cracked pump body when servicing a machine, be sure to look for the possible cause of the excess pressure that damaged it. Allow the engine and hydraulic system to warm up to 120 degrees Fahrenheit or 50 degrees centigrade. With the engine running at maximum governed speed, read and record the pressure and flow meter readings. Slowly close the control valve and bring the pressure up to 1/2 the normal system operating pressure. Again, read and record the pressure and flow meter readings. Now, very slowly and carefully, bring the system up to full pressure. Read and record the pressure and flow meter readings. If the system is warmed up, the reservoir oil level is not low, and the suction filter is not restricted, the pump should be replaced if it pumps less than 85% of new pump specifications. Hydraulic pumps generally last a very long time if the oil is kept clean. However, dirt contamination, rust particles, and metal chips caused by cavitation and aeration can develop wear on a pump's close tolerance metallic surfaces, resulting in lower pressure and lower oil flow. The hydraulic pump drive shaft can progressively fracture over time if the pressure relief valve is set too high, or the shaft and pump body can break instantly if the output oil is blocked and there is no pressure relief. Generally speaking, the higher the pressure and flow rates of a system, the larger the quantity of heat generated. Excessive heat oxidizes the oil and accelerates the hardening of the seals. As seals harden, they lose their elasticity and ability to seal on the shaft. Hydraulic oil runs hotter when the oil in the reservoir is low. Low oil levels have less surface contact with the reservoir to radiate the heat. If the system you're working on shows signs of overheating, look to see if there might be an oil cooler that needs cleaning. Many pump seal failures also result from improper installation. Splines, rough and nicked surfaces can cut the seals during installation. Misaligned seals result in unequal lip pressure that allows dirt to enter the pump. Pump seals can harden or swell from using the wrong hydraulic oil. Swollen seals wear quickly due to the increased friction from the extreme pressure on the rotating shaft. Leakage quickly follows. Pump bodies are also damaged from pressures that exceed manufacturer specifications. Technicians should never raise the pressure beyond the limits set by the manufacturer. Hydraulic pumps are designed and built to give the operator long dependable service when manufacturers' recommended service schedules are followed. Stop the video here and review the principles of hydraulic pumps. Then continue on with hydraulic control valves. Before evaluating a directional control valve or DCV, be sure to run a test on any connecting linkages or electrical control devices connected to the spool. You may feel foolish to later find a disconnected wire or a bent control rod. In the introduction, we showed how spool-type valves are used to direct hydraulic oil to a hydraulic cylinder, and how a relief valve is used to limit the operating pressure. These control valves come in all sizes and shapes, as well as single and multiple arrangements. This set of valves is cast as a single body, while this set is stacked for individual replacement of each valve. Some directional control valves are activated by electric solenoids. This allows the operator to control hydraulic functions more efficiently from a remote location, either manually or with a computer. Control valves are manufactured to a close precision tolerance. Most spools and valve bodies are so closely fitted they do not require any seals between the parts to prevent leakage. Just the smallest amount of dirt in the hydraulic system will act as an abrasive lapping compound that will lead to internal spool leakage. Spool leakage, as well as reduced pump flow, slows down the cycle time of hydraulic machinery. External leaking caused by internal abrasion may not appear until extensive damage has occurred. Valve leaks from internal abrasion are a common cause of slow operating cylinders. Slow cycle time on machinery is the biggest complaint from operators. Each of these items, or any combination of these, could be the cause of a slow cycle time. A low reservoir oil level, a plugged suction filter, a worn pump, a worn spool in a directional control valve, a leaky piston seal, low system relief pressure, low circuit relief pressure, the oil is too cold or the oil is too hot. System pressure on all machinery should be properly adjusted to ensure maximum performance and protection for the hydraulic circuit. To adjust system pressure, select a directional control valve or DCV with no circuit relief and bottom out that cylinder. Continue holding the DCV in the down position to develop maximum system pressure. Slowly turn the adjustment screw until the gauge reads the correct pressure. Then tighten the lock nut. Some circuit relief valves run at a constant maximum pressure. For example, this Jacobson hydraulically sophisticated turf mower. It has a hydrostatic transmission, hydraulic steering, hydraulic cylinders, and hydraulic motors to power the cutting reels. This machine uses a charge pump to maintain a 200 psi inlet pressure to the hydrostatic drive pump when the engine is running at full governed RPM. To test the charge pump pressure on a hydrostatic transmission, first look for a test port provided by the manufacturer. If one is not provided, install a T-fitting with a gauge. To adjust the charge pump circuit relief, warm up the oil to 120 degrees, then raise the RPM to the maximum governed speed. If the pressure is incorrect, adjust the relief valve by slowly tightening the spring to increase the pressure or loosening the spring to reduce the pressure. Some cylinder circuits have additional safety circuit relief valves to prevent damage if excessive force is accidentally applied to the cylinder. If the system pressure is below normal, check whether the directional control valve being stroked has any safety circuit relief valves. If the only time the system pressure drops is when a specific directional control valve is being stroked, that valve's circuit relief valve rather than the system relief valve might be malfunctioning. If you suspect a circuit relief valve is the problem, select a different directional control valve that does not have a safety circuit relief valve and retest the system pressure. In this case, when the problem is isolated to only one circuit, that circuit's relief valve should be tested or adjusted before the system relief or the hydraulic pump is tested. To adjust the circuit relief, install a pressure gauge in the test port the manufacturer provided or install a T-fitting between the pump and the system relief valve. Warm up the hydraulic system and increase engine speed to full governed RPM. After the oil reaches 120 degrees Fahrenheit, slowly turn the adjustment screw 1/8 turn at a time while observing the pressure gauge. The direct acting relief valve shown earlier starts opening or cracking just above 50% of the system pressure it regulates. Because this causes a large drop in oil flow at higher working pressures, it has been replaced in most modern applications by the pilot-operated relief valve. As you can see here, the direct acting relief valve cracks open at a lower pressure than the pilot-operated relief valve. The net result is less oil flow and slower response at higher pressures. Pilot-operated relief valves open very quickly and start cracking at 90% of system pressure, permitting a higher flow rate and faster cycle time at higher pressures. An orifice passage in the pilot relief valve piston allows oil to flow through it to the area above the piston, thus maintaining a pressure balance above and below the piston. At system pressure, the main spring pressure adds to the oil pressure. The combined pressures hold the piston down to seal the relief port. When the pressure above the piston reaches cracking pressure, the adjustable pilot valve opens. Because oil cannot flow through the orifice as fast as its pressure can be relieved through the pilot valve, pressure drops above the piston. The higher pressure below the piston pushes up on the piston, compressing the spring. Oil then flows out the relief port until the system pressure returns above the piston to balance the pressure above and below the piston. When the pressure is balanced, the spring moves the piston down to close off the relief port. Let's see how to check the spool in a directional control valve for internal leakage. Directional control valves can be field tested for internal leakage by pressure loading an actuator like a cylinder, then shutting off the engine and watching for the cylinder to settle. If there are no external leaks, any settling that occurs is caused by internal leakage in the directional control valve circuits. We will see why this is true in Part 7, where we cover cylinders. Try to keep in mind, cylinder pistons will creep down only if the spool in the directional control valve leaks, the circuit relief valve leaks, or, on some machines, the anti-cavitation valve in the circuit relief circuit leaks. Spool leakage can be quickly tested with a hand pump, either on or off the equipment. First, remove the cylinder hoses from the directional control valve. Then, connect the hand pump to the hose port for the spool you suspect is leaking. Pump oil into the port until system pressure is reached. If the port holds pressure, the spool is not leaking. Pressurize the second port in the same manner. If the port does not hold pressure, there are two possible problems. One, the spool may be leaking, or two, the circuit relief may be leaking or operating at too low a pressure. Some circuit reliefs are adjusted by a set screw. While turning the set screw, stroke the hand pump at a rapid rate until the correct pressure is set. Other reliefs are adjusted by adding or removing shims to change pop-off pressure. Another type of relief is the cartridge relief. It is not adjustable and will have to be replaced if it is not operating correctly. We have covered only the simplest and most common types of valves. There are many other types of valves used in hydraulics. By applying simple tests and understanding how they operate, you should be able to accurately test and adjust them. Finally, test procedures shown in this video are not a substitute for manufacturers' test procedures. Be sure to always consult their service or technical manuals for explicit instructions. Stop the video here and review the principles of hydraulic control valves. Then continue on with hydraulic cylinders. If the hydraulic pump, system relief, circuit relief, or the directional control valve is not the reason for slow cylinder operation, you should also check for internal leakage around the piston seals inside the cylinder. Piston seal leakage is not acceptable to most manufacturers. Even a minor amount of leakage will reduce the operating speed and slow down the extension and retraction time of the cylinder rod. Once the technician has determined the hydraulic pump, spool valve, and relief valves are not at fault, cylinder seals can be tested for leakage using system pressure or a hand pump. Extend or retract the piston in the cylinder to be tested. Lower the mechanism to the ground. Shut down the engine and neutralize the hydraulics. Put on an approved face shield and gloves to protect you from hot oil. Remove the hose from the end of the cylinder where the piston is resting. Place the hose in a bucket to collect the oil. Then, pressurize the cylinder for 20 seconds at maximum governed RPM and watch to see if oil is leaking past the piston seals and into the bucket. Excessive leakage will slow down the response time and reduce the power of the cylinder. Abrasion scratches clearly indicate a lack of maintenance. Dirt and wear metals easily damage cylinder walls and piston seals. Piston seals harden with age and heat. Seals that have hardened from heat are not elastic and will not seal against hydraulic oil pressure. Additionally, as they harden, they also easily crack. Cracked seals provide a leaking surface for high-pressure oil, thus reducing the cylinder's power and response time. Before removing a cylinder from the machine, check to see if the retainer is threaded. If so, loosen the retainer by letting the machine stop the cylinder from turning. To prevent scratching the piston's metal sealing surface, be sure to round the corners of any service tool you use when removing or installing seals. There are many types of seals, packings, and wipers used on cylinders. Be sure to check with each manufacturer for replacement parts and correct installation procedures. Some manufacturers use O-ring seals and backup rings next to the O-ring to prevent the O-ring from rolling. Carefully examine the backup rings, as some have a concave surface to fit the O-ring. Be careful when installing the piston into the cylinder bore to prevent the new seals from rolling, folding, cutting, or tearing. When installing lip seals on pumps and motors, be sure the lip of the seal faces inward toward the pressure side. Otherwise, the pressurized oil will leak under the lip. Always contact the manufacturer for correct replacement parts. Will-fit seals and hoses may fit, but may not be compatible with hydraulic oil. There is a common myth that needs to be clarified about leaking cylinder seals. The general belief is that a load will settle if the cylinder piston seals leak. As discussed earlier, even if the piston seals are removed, a load will not settle. To illustrate this point, let's use an excavator with a heavy boom and dipper arm. Before disassembling, all hydraulic pressure trapped in the hydraulic system is neutralized. The hoses are loosened and removed. The oil is carefully caught in a container. The fitting is redirected to drain the oil into the container. The cylinder rod seal retainer is loosened. The rod pin is removed. The cylinder rod seal retainer and piston assembly are removed. The piston ring seals are removed. The piston and rod assembly are reinstalled in the cylinder without piston seals. The cylinder rod is pinned and the hoses are connected. Next, the engine is started and the boom's directional control valve is held in the lift position to fill the cylinder with oil. Oil passes by the piston and purges the air on the retraction side of the piston. This removes all air. The engine is shut down. Caps are put on the cylinder hose fittings and the jack is removed. 4 hours later, the boom, without piston seals, is still in the air. Since the larger volume of oil below the piston cannot fit into the smaller volume above the piston cannot move in the cylinder. In review, keep two primary principles in mind at all times. First, pumps create flow, and the flow rate affects the speed of all cylinders and motors. Flow rates depend on pump size and engine speed. Manufacturers of engine-driven machinery specify the pump flow at the engine's governed RPM. Second, restrictions cause pressure, and the pressure applied determines the working force or lifting power of a cylinder. Weak functions are generally caused by low pressure and not low pump flow. In addition, if a load settles, the control valve must be leaking, even if the piston seals also leak. In this study, we do not recommend any particular test sequence. Keep in mind, the correct test sequence will vary according to the problem. Check with each equipment manufacturer's service manual for diagnostic flow charts and correct procedures to follow when making direct pump tests and T-tests. We have included a diagnostic worksheet to help you analyze your information. In this program, we have covered the fundamentals of fluid power systems and their basic components. As you can see, hydraulic applications are incorporated in a wide variety of equipment used throughout the world. It is due to technicians like you that this equipment can be well maintained for safe, smooth, and reliable operation.